So here again, a bit more detail is the calcium energy levels, which I'll be talking about, and the various possible qubits. So can I borrow your laser?
Yeah, sure.
Okay, so here's the ground level. That's the Zeeman spinning, which we impose from the lab by bringing magnetic field, and immediately that means it's bad because we in the lab can't control magnetic fields that perfectly. It's much nicer to use the intrinsic high-performance splitting here. Here's the optical qubits, and these other levels around here are important for operations of detecting qubits or laser calling it. So we use these two. This is a manifold of levels here, SR 3.5, D3 halves. Which the ion cycles around when we're calling it. That's how we get it in the trap and keep it there in the first place. These two up here are important for detecting the qubit, as I'll explain later. What does an ion trap look like? This is a classic example of an ion trap. I guess I'd call it the retro version now, as most people don't use exactly this kind of trap for quantum information applications. I'll talk to you more about different kinds of traps in the third lecture when we talk about scaling up. But it's easy enough to see how this one works. In detail, there's an end view. These things are electrodes in the vacuum system. There's an end view. The only trick of it is transverse confinement. You can't make an electric field which confines in all three dimensions. Right? So the trick in a power trap, an ion trap, is to have opposite electrodes here with opposite phase of RF voltage. So what you do simply is generate instantaneously a saddle potential. So the charged particle will be trapped there, but there's an escape down inside the saddle, but then you flip this saddle upside down. Just do that very rapidly, more quickly than your charged particles will escape. That can trap anything, including charged atoms, ions, which is what we like. And then at the end here, you have these certain DC end caps, which just close the escape routes along that long axis of the trap. And if you build your trap in this linear geometry, the point of doing that is that your ions make it weaker the axial direction. Your ions sit in this nice linear crystal, like that. That's a row of ions in our system. And by simply by adjusting the DC voltages on the end caps, you can adjust the spacing here. And for typical situations, you can make that spacing about 10 microns. And this is the original idea of the ion trap quantum information processing, suggested back in 1995 by Sirach and Zoller, was that this spacing is big enough you can focus laser beams to about a micron size, individually address those different ions. That satisfies one of your important Da Vinci criteria about having single qubit addressability. Laser webbing is such you can easily focus it to a micron. That's been used to great effect in the Innsbruck system, where their optical qubit transition that they're using, because it's optical, they drive directly with a laser. It's very difficult to drive with a laser. It's technically challenging because that upper level, you want to have a long lifetime, means that transition is very narrow, right, to 1 hertz natural language. So you've got to have a laser which is stabilized to 1 hertz frequency stability, which is pretty challenging. Another challenging thing is even if they can focus the laser down, in principle, in practice it's very difficult to get it to address individual ions. There's always a little bit of light scattered onto the neighbouring ions. So that's one of the challenges with this idea of putting more and more ions onto one ion trap region. And that's why most people don't see that as a route to scalability for a large sort of 1,000 qubit processing machine. That's what the actual physical thing looks like. This one here we used to use in Oxford. It's just made in the workshop. It's very much a macroscopic device. You scale up there. These white blocks here are about 20 millimeters in size, to be idea. So the ions here sit about 1 millimeter from the nearest electrode surface. So for our purposes, you don't really need to know anything more about ion traps. Okay, they just trap and confine charged ions, and to the ion looks like a 3-dimensional harmonic oscillator. Okay, and in fact, for most of our purposes, you don't need to worry about the X and Y harmonic oscillators. We're just going to be interested in the Z harmonic oscillator along there. And in fact, even that we're not going to be interested in for this lecture, because I'm just talking about single qubits and internal state manipulations. So when we come to talking about how two qubits interact, it's that harmonic oscillator potential, the shared normal modes between these ions in the trap, which are the key to the as you probably know. Okay, so how do we make our ions in the first place? We use a process called photoionization. We take neutral calcium and spray it towards the trap, and with two transitions we promote one electron to the continuum. And that's the picture that you just heat up an oven and spray these atoms across the trapping region, and you come in with your lasers here. And it's a very nice example of something that about 30 years ago, this was the sort of cutting-edge laser spectroscopy. It was Doppler-free laser spectroscopy, right? Having your laser beam perpendicular to your atomic beam. Peter's already mentioning atomic beam machines. This is sort of almost a basic version of atomic beam machine for laser spectroscopy. You get rid of the Doppler shifts by having the motion of the atoms perpendicular, and you get narrow resonances like this. The purpose of this for us, the interest is really to be able to select different isotopes of calcium. I mentioned you're interested in this calcium-43 guy, which has a real pain in the neck practical problem, but it's only 0.1% abundant. So there's not many calcium-43 atoms coming out of that carbon, but luckily we only need one or two of them at a time. So it's too difficult, but you zoom in and you can see them. And amazingly, you can use that technique and load pure so-called crystals of calcium-43, even though you've got all these other isotopes which are much more abundant. It's a nice example of something that was 20 or 30 years ago. It was a cutting-edge research. It's now just a useful tool for us. That's technology moving on. It's now a tool for us to load our ion trap. Okay, so how do we cool and prepare internal states? And the answer to laser cooling is simple Doppler laser cooling. So one example of how you can do that is if you have this sort of energy level structure. You have a cycling transition here between the n is plus a half, there's plus 3 halves states on that particular transition there. If you apply circularly polarized light to that transition, then the ion cycles between those two states only and fluoresces. And if the laser is really tuned, you get Doppler cooling. And when you turn off that laser, the ion will decay and it will always be found in that state. So you've paired one single state particle pump. A slightly different method which is often used and it's not actually more important and necessary in calcium, is just use this transition instead for not for the laser cooling but the Oxford pumping. Same principle, except when the ion decays to this state over here, it can decay either way. When it decays over there, that state is dark to the light because that cannot absorb one photon of angular momentum from that light beam. Cannot increase its mj quantum number because there's only mj plus a half. So that's simple to call. You might like to think about if you optically pump to one of those states whether you've achieved zero temperature or not. If you pump optically, does optical pumping get you to absolute zero immediately? How do you then manipulate the qubit states? So there's a couple of different ways. So if we're talking about, on this side it's hyperfine qubit down to ground state, this is an optical qubit. So I guess the optical qubit is more obvious. You just have to drive this difficult to drive narrow electric quadrupole transition, and you need to be able to drive it with a Rabi frequency fastened over the 1 second lifetime of that upper state. Obviously one of those two things to a qubit faster than 1 second, so you can't do that even. So you can, with I guess in lab terms, a few, maybe 10 milliwatts of laser power focused onto an ion, you can drive that transition with Rabi frequencies, maybe 100 kilohertz. So that's you can definitely drive qubit rotations on a Bloch sphere much faster than the qubit lifetime. But it needs, that's in lab terms a reasonably significant laser power. So if you think about scaling this thing up. If we've got a ground state qubit, hyperfine or Zeeman, we can drive the transitions in two ways, either directly by the radio frequency or microwave transition. Okay, so we can apply microwaves. The obvious problem there is how would I address different qubits with microwaves, given a microwave wavelength. In our case, we've got a 3 gigahertz transition, that's a 10 centimeter wavelength. That seems like there's no way you can address the other. So I'll tell you more about that in my final lecture about tricks about how you can use that. And in fact, Diana Ford, who's here from the Oxford group, has a poster all about this. The other way, which has been used much more commonly, is to use Raman laser beams. So we have 2 laser beams detuned a long way from these allowed transitions. So the laser beams don't scatter photons by normal photon scattering, but they drive a Raman transition via a sort of virtual level up here. And then you only care about the difference frequency between those 2 laser beams. Okay, so you don't need to, even though you're driving an effective transition here, which is very narrow because there's no spontaneous decay between those two states, unlike this narrow transition, you only care about the difference frequency between the laser groups. In the lab, it's very easy to put on a very precise difference frequency, even if your laser is not very well stabilized in absolute frequency. And so this is used very commonly to manipulate internal states. And also, the key thing is that the laser can impart momentum more easily to the ions, and that's the key to two-qubit manipulations. So the reason that can happen is because laser photons carry a reasonable amount of momentum. Okay, you know that already because you can cool atoms by laser cooling, right? And that's the same process you're using, momentum from the optical photons. So we can manipulate internal qubit states, but also affect the motion, and that's I should say key for quantum physics. Just coming back to the state preparation, here's one of the tricks that we can use in the lab. So I told you about optical pumping being key to preparing a definite quantum state. Now, if we're thinking in terms of quantum computing, ultimately we need to do all these operations really, really well. Okay? We need to aim for these high fidelities, the level of somewhere like, well, at least 99% for state preparation, preferably 99.9 or 99.99% fidelity, in order to be able to implement the ideas of quantum error correction and scaling up quantum computers. It's really tough to get optical polarization into a vacuum system with that high precision. If the polarization isn't perfect, then this state here is not perfectly dark to the laser light. Okay, and you'll end up, so this is these blocks here, especially represent the population, the probability of the ion getting across the block. And so this is the ground state manifold, calcium 43, and these are different MF states in the ground state manifold. We like to enter a little bit because of imperfections in the direction of that light. So a trick we can use with our microwaves, for example, is to take those two states and apply on those two transitions at slightly different microwave frequencies, pi pods. Okay, so that's just a rotation 180 degrees, and you've got the sphere of those two qubits, right? And then you turn the laser light on again, and that recaptures this little population you've lost. You can cycle that around as many times as you like, and you get better and better population progression in that endpoint. So that's a nice cunning trick which allows you to do something robustly against typical real-world imperfections. Okay, so I told you that hyperfine qubits were nice because they were well-lived. So here's an example of a particular pair of states that we use in the ground manifold of calcium 43. We like these states because they have MF equals 0. That means they have no first order Zeeman shift. They're insensitive to magnetic fields of first order. That's very important because you can never get rid of magnetic field fluctuations in time. Okay? So all these other states will be wobbling around a little bit in frequency, and of course in a qubit that's really bad, right? I mean, if you want to think about that, there's a phase between the two qubit stages building up in the block sphere. There's there's rotations about the z-axis which are just jiggling about and you're uncontrolled all the time. So these states are nice. And you can Rabi flop on this transition with microwaves for long times and get many hundreds of flops. In fact, this is pretty old data. We can do much better. We can now flop for probably a second on this state without seeing any serious defect or similar magnetic field independent state. These states are often called atomic clock states. So it's exactly this kind of transition, because it's insensitive to perturbations in the lab, that we use to define the unit of time. It's like second. It's the ground state manifold of cesium. Looks exactly like this, in fact. It's the same nuclear spin as calcium plus, that's calcium 43. And that's how you define the signal by an atomic clock microfine transition at about 10 gigahertz, 9 gigahertz in cesium. And that means they make good qubit states, right? Again, they're insensitive environmental noise. And building good qubits is very much like building a good atomic clock. In fact, requires very good atomic clock to calibrate. So how do we calibrate the coherence of a state like that? So if you just look at things like Rabi flopping here, you can see it starts to get a bit messy over there compared with the blue theory curve. That might be due to intrinsic decoding to the qubit. It might be just due to the fact that your microwave power is not very robust. So a better way to classic way to have any qubit is the Ramsey experiment. So we have 5 by 2 pulse, and then wait time, and then 5 by 2 pulse, and 5 by 2 pulse puts your qubit in superposition up and down, and the second 5 by 2 pulse is supposed to then complete the rotation on the Hawke sphere from the north pole to the south pole of the Hawke sphere from upstate to downstate. And if it doesn't, that means while your qubit is in a superposition state, it's been jiggled around by some decoherence mechanism. So measuring the contrast of Ramsey fringes is the classic way to measure coherence of a qubit. And here are some Ramsey fringes. And so you pay attention to the numbers in the scale. This is the D-tune in hertz at 3 billion hertz. Okay, so this is like atomic clock physics where you're tying down frequency, extreme frequency. And this is the contrast of the fringes. These error bars, by the way, just standard deviation from a shot noise limit. If you think we're doing this with one single ion, like one qubit. When you measure it once, what answer do you get? Do I get up or down? You have to measure it hundreds of times to find out what the probability of that qubit is. So these experiments are pretty demanding. This is a third of a second every single shot of the experiment. Then you do that hundreds of times, that gives you one data point here, and then you move on to the next frequency to do it again. So the stability demands in the experiment to maintain coherence and so on. Tricks to get these fringes. As I say, it's like a atomic clock. And that particular qubit had a coherence number of about a second. I'll show you some even more impressive recent data later on. You can do a bit better than that by protecting the memory qubit with a spin echo pulse. And this may or may not be something you will do in a real quantum computer, but it's very often the way people quote coherence time is actually in different systems, like people that are looking at NMR systems or solid state. They often do the measurements this way because it's simply too difficult to measure the T2 coherence time because it's often too short. What spin echo does is protection against the decoherence mechanisms, and it's, I'm sure you've come across that method before. So this is a similar experiment where we have a control experiment and a real experiment with 1 second. That's the red and the black data and physics curves here. And again, this is you adjust the phase of one of these, the second Ramsey pulse, and just basically maps out some frequency. So you're just seeing quantum coherence here over the 1 second time scale. And the key thing here is that you cannot see any difference. There is no statistically significant difference between those two experiments. That means the coherence has been maintained. Statistically here, I think it's a level of about 98 or 99% over 1 second. If you wanted to try and extrapolate that into a decoherence lifetime or T2 time, it would be something like a minute. So these are high quality qubits. Okay, so I'm going to talk now about qubit state detection, and probably for most of the rest of the talk about this. And that's obviously the last thing is you've got to initialize our qubits, we've got to manipulate them, we've got to read them out, it's a crucial thing. And I guess I should admit to having some long-term obsession with qubit readouts. Always been thinking of different ways of reading out qubits and our particular qubits. And that dates back to when we first started these experiments. We're working with this calcium-40 qubit, where I mentioned to you that that's in the ground state, but the energy of these two states are very close together. That made it very difficult to discriminate and read out the state. All kinds of crazy schemes to read out a qubit. We're eventually able to do it. But since then we can, particularly when we move to this qubit in different ions, we can do this thing much better. And there's some nice tricks you can use here. The simple way, the easy way to do qubit readout is to take an ion which has a structure like this. So this is not calcium, this would be like beryllium or magnesium ions. The key difference here, they don't have those low-lying D states sitting over there, which complicate the different possible transitions that happen. There's not a simple closed cycling transition. So this is exactly the same transition I mentioned earlier, which you'd use to optically pump, repair, laser cool, and you can use the same transition to read out your qubit state using the tunable laser close to resonance of that transition, and it cycles, and the dash line here is spontaneous decay. It's photons. You collect some of those with a big lens and a detector, and you can see where the ion is fluorescing. If it's in the 1 qubit state, it will fluoresce. If it's in the 0 qubit state, the laser is detuned by where that splitting is down there. If it's microfine splitting, it's typically 50 gigahertz. And therefore that state does not scatter photons, only scatters tiny number of photons, or photons with a very small probability. So that the gain there is to collect enough photons to tell whether your ion is in that state before you off-resonantly excite the other qubit states. You've got to sort of brighten a dark state. So I mentioned you can't do that in an atom like calcium. We have these D states, but it turns out those D states give you a even better way of measuring the state. So the level diagram is more complicated here, but the method is to use electron shelving, and we use one of these D states called D5 halves over here, and we call it a shelf because that's not coupled to the usual laser cooling manifold of transitions that we use. So you can excite fluorescence from your ion without knocking it off that shelf. Okay? So the trick is to get it into that shelf in a qubit state dependent way. So we've got two different qubit states. One is, in this case, down here in the ground level, and the other in one hyperfine manifold, and the other qubit state is up in the other hyperfine manifold. And so it's the same principle. Because this transition isn't closed, we have to sort of plug the gap. It can decay either over here, which is part of the laser cooling manifold, that manifold, dark qubit bright. We have to plug that gap with particular polarization of the pumping lasers, and we then make a sort of quasi-cycling transition and force the qubit to decay over into this shelf. If we didn't plug this gap, it would only decay at about 90% of the time. That's no good for aiming for much higher fidelity. So it turns out you can get to the sort of 99.9% level in state detection fidelity, or at least mapping to get from that state over to there. So you can transfer your qubit over, or one of the qubit states selectively for that shelf. And then you just turn on your normal laser cooling, suppression lasers, and look for fluorescence of your ion. So it's a two-step lead-up process. Okay? First is to transfer to this shelf, and then to fluoresce. So here's a simplified systematic way of doing that. And I'm going to talk now about the second stage of that readout process where we look for fluorescence. So there's our shelf right there. These stages about 1 second lifetime, and there's the ground state of the ion. And if you're using, as in the Innsbruck experiments I mentioned, that optical qubit, then these are already your qubit states. But you don't have to have that transfer of the ion to the shelf. And as I say, you turn your usual laser cooling lasers, and here's your ion in the trap. It scatters and fluoresces, and you can see it in the camera or photon multiplier, and you get lots of photons. And this is certainly not a new method. It was first proposed back in the 1980s, well before people even thought of quantum computers in the context of atomic clock, in fact, because this is a narrow optical transition. And in the last few years, you can now use that kind of transition in particular ions to build the best atomic clocks in the world, which are now better than in fact, better than the cesium clocks. So they're better than the definition of time. So at some point, somebody's going to have to be moved to using optical clocks to define the SI second, and they're a fantastic precision. I mean, the important thing here, I guess, is that you've got a transition frequency which is about 10 to the 15 hertz, and a transition line width which is in this system about 1 hertz. So imagine measuring that transition, the width of that transition over its absolute value is already 10 to the 15. In some systems that width can be even lower, down to approaching sort of millihertz levels. And so the systematic uncertainties in those atomic clocks, which have been developed in the Weiland group, mostly by a guy called Tim Rosenbaum, they're now 10 to the minus 18 level. So it's a fantastic level of precision. Anyway, I digress. Obviously, they use the same method for state detection, atomic clock transition. But for qubits, the challenge here is what you've got to do is average this fluorescent signal for long enough to get the signal to noise before your dark qubit state becomes bright. In this case, it will decay on average after 1 second into the bright state, or then the dark state will become bright and vice versa. So, and that's not just atomic qubits. If you think about it, any kind of qubit, some electronic system, you've always got some signal, and it's obviously you want to average for some time to improve the synchronize, but there's always some process which will flip your qubit state. So that's the kind of battle you're always playing. Quantitatively, this is what the system looks like when you do this state detection. The process is very simple. You just count photons and photons for a certain amount of time, and if you do zillions and zillions of experiments, you build up histograms like this. If you compare your qubit in the bright state, you get this green histogram. Yes, there's just a number of counts, and sometimes you get time interval, number of events up here. And that green thing, that's actually a Poisson distribution. It doesn't look very Poissonian because it's on a log scale. The dashed line there is the Poisson distribution theory curve. And the other one is a bit funny because it would be just a Poisson distribution down here, but these over here are the events where that qubit started out dark and became bright. Okay, so all you do is you stick a detection threshold at some particular count value here, which minimises the error. And what I mean by the error is the tail of the green distribution is below that threshold and the tail of the red one is above it. So that's the standard way everyone does their state detection. And we did some experiments on this a few years ago, and we thought, well, nobody's actually seen how high a precision you can get to here. Let's see what we can get this error down to. And we looked carefully at this, and we couldn't quite match the data down here. And we discovered that if you just take the photon multiplier with no ion or anything in the track at all, you still don't get a Poissonian distribution of counts. You get sort of black curve here, this long tail. And this is, I've just reminded us of Peter mentioning cosmic rays in his talk. It turns out that these events down here are due to bursts of counts on your detector, which are cosmic ray events. And it turns out that about 10% of your qubit detection error in that particular example came from cosmic ray events. So I thought this was an amusing thing when we first observed this. And so what we looked at was that you can get some more information about these your qubit state if you don't just sit there and count photons for a certain amount of time, but you actually time step and time tag. Okay, so the idea is then that you might hope to see not only things like these cosmic ray events, but you might hope to see also occasions when your qubit started out dark and became bright. Okay, so you get events like this. If you start out with a qubit which is dark, you just get basically no clicks. This is time across here. It's one click of background counts because nothing is perfect. If your ion starts out bright, you get lots of clicks. But occasionally you see things like this where it seems to start out dark and then becomes bright. Okay. And very occasionally you see things like these cosmic ray events where you see a big burst. And now it basically becomes a statistical problem to tell whether you can tell the difference between these different kinds of events, and surely the time information here, the extra information must help you improve your detection fidelity or reliability, and indeed it does. In fact, the theory of this stuff had been worked out before by a guy called Chris Langer, and was working in the Boulder group at the time. He said, all you do is a simple experiment, so you prepare the qubit and then read it and look at the times of arrival of your photon. And you do this maximum likelihood analysis of this. You say, what's the likelihood that that particular set of times that you measured came from an ion that started out bright? Compare that with the likelihood that the particular set of times came from an ion that was dark. And if the bright likelihood is bigger than the dark likelihood, you say it's bright and vice versa. That's simple maximum likelihood analysis. The only problem is when we looked at his paper on how to do this, this was the mathematical expression for how you calculate the likelihood from your data set. And so, there are two problems with this. One was simply that, okay, well, this is crazy in practice, you're never ever going to use this in practice in some real quantum computer because it's going to take you longer to do this calculation than your qubits are going to be alive for when you care about the measurement result. And the second problem is, of course, that being a poor, slow experimentalist, there's no hope I could understand what was going on here and whether he made a mistake. But it turns out actually that it's a bear. It turns out what we actually do in the experiment is we don't actually, because our experiment is not that great, we don't time tag these photons with fantastic precision. Like say Dustin, you might doing your cryptography, time tagging these photons to nanosecond precision. And we just counted them in discrete time intervals. It turns out in the maths is much easier. You can calculate the likelihood. All it is it's just a product of probabilities. You've got these counts, which are either 0 or occasionally you get 1s and 2s and so on with qubits. It's just Poissonian distributed photon counts. Okay? So Peter just told us that atoms don't really emit Poisson distributed photons. And that's true at some level at the level where you care about the G2 anti-correlation functions. But the timescale that occurs on is the timescale of the upper level of the fluorescence state in the atom. And that's typically a few nanoseconds. So we're looking at much longer timescales here. We only detect a small fraction of the photons that come out. We're looking at collecting photons in timescales of microseconds rather than nanoscales, so nanoseconds. Everything is very, very Poissonian. So the likelihood of it being right is just a simple product of probabilities for each of those time pins. The likelihood that it's dark is a bit more complicated because you've got to account for the probability that it will decay, but it's still pretty simple. You just take the probability the ion has not decayed in this detection line, which is actually quite close to 1, because the whole detection time here is quite small compared with the upper state lifetime. So TB is the entire detection time, tau is the upper state lifetime. And that's just the first term of obviously exponential expansion. And that's just your product of probabilities again. And you have to sum over, add on the possibilities that it's decayed in each different sub-bin. So you have now a sum over impossible sub-bins that starts out dark for the first J sub-bins and then it becomes bright for the rest of the measurement rate. So it turns out this is a very nice way of doing your state detection. It's much more robust than a simple counting for a fixed amount of time. Robust against things like cosmic ray events, things like drifts in the fluorescence. And so when you run various different statistical analyses on the same data set here, you can see that if you do the simple threshold method, so this is the readout error, average between the bright and dark states, as a function of your detection time. So always in operations or qubits, there's always some error time trade-off. Okay, you always want to do things faster, and that usually increases your error. So you can see that if you try and do things really fast here, this error starts to increase against the log scale, starts to increase exponentially fast, so that's bad. But you come down here, there's some optimum time, and if you count too long with a simple threshold method, then the error starts going up again as you use this maximum likelihood technique with the extra information that comes down, and it stays down here, and it gets down just below 10 to the minus 4. So this was a nice thing when we first did this, because this was the first qubit operation that we saw to reach this sort of 10 to the minus 4 error level that people long talked about. So, of course, this isn't the easiest thing. We always start with the easiest thing. And one other nice thing you can do when you have this time information is that you can do a sort of real-time adaptive analysis. And you can actually, when these photons are coming in and you're counting them, you can actually stop adaptively if you've got enough information. So you can actually calculate the amount of information you've got using Bayes' theorem up here. And you can say, right, when I've got enough information, I can stop. So that effectively gives you a speed up when you reach this sort of level of 99.99% fidelity, about 150 microseconds. And this is just comparisons with lots and lots of different qubit measurements, things in all sorts of different systems. So we've got ions and atoms and photons and superconducting phase flux and charged qubits and so on. And again, you can see there's a sort of it's quite a strong fidelity or error time trade-off here. You can do things really fast in solid-state systems. Right? And this is always the selling point of solid-state systems for quantum information. To do things fast, you can't, at least not yet, do things with very high fidelity. And in fact, if you really cared, I don't think you do, but if you really cared, you could improve this quite significantly, because it's actually limited by the net photon collection efficiency. In a typical experimental error experiment, it's 0.2%. It wouldn't be difficult to just have a bigger lens in your ion trap and put all those photons, and you could easily improve that. But I don't think you actually care to, and it's necessary to do. And I guess another relevant timescale point here is what the decoherence times are. So, for example, for trapped ions, the decoherence timescale is much, much longer than this sort of measurement timescale. For superconducting qubits, it's not, it's more of a struggle to get that big gap in timescales between qubit operations. We'll see this again when I talk about 2-qubit gates in the next lecture. Big gap in timescales between how long it takes you to do something useful and how long you can keep your qubit coherence alive. So this method is called time arrival result detection of ion states. And that was coined by Alice Barrow, who did this work when she was a big doctor school. Of course, she also thought that, the TARDIS, it doesn't just give you voyages through time, it gives you voyages through space. So there was an actual extension of this, which was to do a similar experiment with a camera, and we call this thing a qubit because it's half a qubit. It's 4 qubits. In computing, you do 4 bits a minute. So you prepare all 16 possible states and analyze these with a camera. And this is just a classical, just like the previous thing, it's just a classical information problem area, how you best use the information. The only wrinkle here is that there's no way anyone in the world, as far as I know, can prepare those states accurately enough to measure how well you're doing the detection. So there's also this problem in trying to measure things like qubit preparation and measurement. Right? You can't separate preparation from measurement. Or you can, but it's tricky. So there's another cunning trick here where you do that, which is that you make the measurement several times. So you prepare a state like this randomly, and you measure several times in a row, and if all those measurements agree with each other, you have very high confidence that you know what you're doing. And so basically sort of doing control experiment. What we're interested in is how well you can do this in spite of the crosstalk. So if you take a typical image of these ions, then imperfections in your imaging system mean that there's crosstalk between neighbouring ions at the level of about 4%. And you think how we can wipe out the chance of doing high fidelity detection. Turns out that's not true. If you're cunning about how you use the information, because you know something about the distribution of that light on that camera. So because you know that, you can do much better than you might expect. And you can actually get these just different analysis methods applied to the same data set. You can actually get this detection area down to the 10 to the minus 5s. That's the area just due to this crosstalk. You've still got an area of 10 to the minus 4 due to the fundamental limitations of QuiCC K. So that's this was a nice trick using the camera. And this best method down here also just uses information about the nearest neighbours here. So it's a sort of scalable system. You can imagine scaling this to an almost 2-dimensional array of ions in this world. Okay, so I shall stop there. And after the break, I'll talk about the qubit interactions. And as I said, this depends, the key to these is the motion in the ion trap qubit. So this is the video, I think this one came from the integral ion trap group of long crystals, linear traps, and you can see that this is the centre of mass mode of motion. So these are just coupled harmonic oscillators, just like masses with springs in between. Essentially, they're moving back and forth, and their separation is staying constant in the centre of mass mode. This is the other, or another normal mode of the axial motion of this 7-ion crystal, which is a breathing stretch mode of motion where their separation is changing by a large amount. And these shared modes of motion are the key to moving quantum information between the qubits. And that's what I'll talk about next. Thank you.